like terms. Looking for is, do we have any letters, any variables that exactly match? And in this case, hopefully you're thinking, no, we can't simplify this one, even though it is an example of one that does have different terms. Exactly means to the exact same power and the exact same letter. Let's look down here. Let's see, here I have a 3x. As I go left to right, do I have any other terms that have just a plain x to the power of 1? Let's see, not 4, that doesn't even have a letter. That's a regular piece. Right here we have one with an x. I'm going to put a mark under that one. Let's keep reading. Okay, let's see. So that 9, that doesn't. And that one right there, this is not considered a like term to my 3x and my negative 7x because it has a 2 on it. So again, you need same power, same letter. Everything has to match exactly. So here we have 7 and a 3. And we put it together like as if it were apples and oranges. You put the apples together, you put the oranges together. So here, since we have these two matching pieces, we can combine the numbers in front. We have a 3 and a negative 7. Let's see, that sounds like a difference of 4. Again, we're putting together 3x minus 7x. Looking at the coefficient, the number in front, we say 7 minus 3 is 4. The one that had the highest quantity was negative, so put a negative in front. That looks like a negative 4x. Okay. Moving on, we'll say, okay, well, let's see. I've got a number here with nothing, with no letters on it, and that matches my 9. So we just put them together. They match. 9 plus 4, 9, 10, 11, 12, 13. Sounds good. Positive, since they're both positive. And as far as this one goes, I'll put a little triangle under it because I do use symbols as I simplify my things so I don't leave any pieces or any terms off. With that one, there's nothing that matches. So minus x squared. Now as you look at this, notice it is fully simplified. Because x to the first power is not the same as x to the second power. That power, that floating number, does make a big difference. And of course 13 doesn't even have a letter. It's not even in the game. It's just hanging out right here, attached by a plus. This is fully simplified. Let's look at another example. Again, remembering we're looking for same letters to the same power. And when they qualify that, when they do exactly match, we put them together. We just add or subtract like we usually would, since they already match, since they go together. Okay, so left to right, let's see, 3y. So I have a normal y to the first power. Going across here, let's see, that doesn't match. That one right there does, because that's a plain y, that's a plain y. Here's another plain y. And again, the number in front that we call the coefficient, that's what we put together. So we have 3 minus 7 plus 2. That's what should be in your thought bubble right now. 3 minus 7, that sounds like a 4 that's going to be negative, plus 2. When I put those two together, I'm going to get a 2 that's negative. So I'll come over here and I'm going to say negative 2y is my first new piece as I clean house here. Okay, and then we have negative 12x. Since there's nothing else with the x piece. And again, these are different letters altogether, so you definitely know you can't put those together. We've simplified. Here's another example. It's kind of tricky, so I'll give you a second to look at it before I start working it. Noticing here that we have negative 15xy. The first thing you should ask yourself is, do I have a match for it? So I'm looking for something with an x to the first, a y to the first exactly. So same power, same letters. And of course also I'm hoping here that you remember that when things are attached like that, just like on that example we did earlier, there's really an invisible multiplication here. Holding these pieces, holding them together within themselves, okay? So as you go over here, it's really tempting to say no, based on the exactly thing that we're looking for. But it actually does match. This is multiplication. In other words, I could have written that same number that way, because it's just a bunch of stuff attached by multiply. We'll discuss later on the fact that we'll remind ourselves that multiplication in the order doesn't matter. So when you're looking for like terms, the letters can be jumbled up. You're mostly saying, I need a plain x to the power of 1. I need a plain y to the power of 1. Do I have that? Exactly. Yeah, I do. See, look, x to the power of 1, y to the power of 1. Exactly in this piece right here. So as we put it together, we have 15 and a 3. Different signs, so I subtract, getting a 12. And the 12 is negative since the 15 had more weight there. And I'm just going to write xy. It doesn't matter. If you want to write yx, who cares? Generally, when you're looking and checking answers, ABC order is used. That's kind of trivial, but that's just something you'll notice if you use your book at the back of it to look at your answers. And that negative y, well guys, even though it's a y to the first, which is in both of these pieces, it doesn't have the x part. So it doesn't match exactly. It doesn't have all of the pieces it needs to match exactly. So we just write minus y. And this is fully simplified. Notice something for me here. Just a note that I'd like you to make. Since we've been talking about coefficients, numbers in front of the letter, in front of that negative y, note for me that there's an invisible 1. Okay? Since we know that a 1 times something doesn't change it, in math we do like to say there's an invisible 1 there. That's not really relevant here, but it will be relevant later. Okay. Here's our last example with this whole idea of simplifying, putting like terms together that we like to do with addition and subtraction. So looking here at this, we have AB, AB. This matches exactly. So what's the deal? We have a negative and a positive, which means I subtract. Let's see, 7 minus 7. That would be a 0 AB, right? Now wait a second. 0, we said there's a multiplication in between every single part. So 0 times something times something. Oh. That looks like a plain 0 to me. So technically 0 AB is what you get when you combine those two, which is the same thing as just saying 0. Now let's remember some basic stuff about adding and subtracting. Some properties that you've probably taken for granted for a very long time. The two main ones we're going to talk about are associative and commutative. So let me remind you of something. Let's say you had 2 plus 3 equals 5. Please note for me that 3 plus 2 will still give you 5. My ability to change the order of these numbers, to flip the 3 and 2, to commute them around that plus, is called commutative. My numbers can flip, and my answer is still the same. This property, this idea that order does not matter, also holds with multiplication. For example, 2 times 4 is 8, and 4 times 2 is still 8. So with multiplication and addition, I have this property where I can flip my numbers. Flipping numbers is okay. Okay? Associative is just a level up from that. It's still talking about the order and expressing that the order does not matter with multiplication and addition. Order with associative talking about parentheses or grouping, how things associate or group with one another. So for associative, we'll say, okay, well, what if I had more than just 2 plus 3? What if I had 2 plus 3 plus 4? And let's say I'm going to group these two to give you priority with order of operations. So that you'd then say 2 plus 3 is 5 plus 4. Well, of course, you'd get 9 here. How does that compare then to the same exact string of addition where it's all the same operation being add in this problem, and I'm going to move my parentheses. I'm going to regroup this setup. Let's see, 3 plus 4 is 7. Bring down my 2. We still have addition happening. And again, yes, we're getting 9. That same pattern will also hold again with multiplication. And the point here is that whether you're calling it associative or commutative, When you have plus or multiplication, and it's just one of them, notice this one right here was only multiply, this one right here was only addition. When you have just that one type throughout the problem, order is not important. Why is this important in algebra? Why do I point this out now? Well, because sometimes you may choose to do things in a different order and you need to know it's okay. Of course, in saying that, I want you to note something for me. If you had 7 minus 2, subtraction does not hold with the order idea. I cannot flip these two numbers around the operation. 7 minus 2 is clearly not the same as 2 minus 7. Let's see, over here I get a positive 5. Over here I get a negative 5. They are not the same. That is not okay. You cannot flip it, okay? But that original 7 minus 2, if I now rewrite it using some of the integer knowledge I have about positives and negatives, I can write it as 7 and a negative 2. Very significant. Now that I have that addition, that property that I just reminded you of, where order doesn't matter, now applies. In other words, that's the same as negative 2 and positive 7. Reason being that that subtraction, I'm attaching it to the number, so I'm making it safe to mix up my order. I'm making it safe to put the negative 2 first. So again, it's quite different than the top thing up here that I showed you. In this case, I add an and in between so that I can do more tricks later. Here are examples from the text. Here this reads 12 times 5 times x, straight across. Even though you have the parentheses trying to force you to do what's inside first, we saw just a moment ago that that kind of prioritizing, when it's all just straight multiplication attaching, is not necessary. Order does not matter, so therefore I can drop my parentheses and just write multiplication straight across, doing multiply to the 2 that it comes more naturally to do it with. So here we have 60 times x as our answer. Let's look at another example. Once again, they're trying to trick us with this idea of parentheses, trying to give priority to these two against this fraction. But again, it's all multiply. Between the 8 and a is a multiply, and between these parentheses is a multiply. So I can literally rewrite it that way. Now hopefully you can see that since it's just multiply, you can do those two numbers and just attach the a. In other words, thought bubble, negative 8 times negative 3/4 is what I can look at. Remembering the trick from earlier, that if you want to start reducing your fractions while you're multiplying, then multiply plays pretty nice with that. Between the 8 and 4, I can pull out a 4 on top and bottom. So if I pull out a 4 from this, I'm going to be left with a negative 2, and down here I'll be left with a 1. So negative 2 times negative 3 gives me a positive 6, and then 1 times 1 on the bottom, I'm just getting a 6. So again, when I put those two together, I get positive 6. A still holds on by multiplication.